All right, so in this video, I'm going to talk about what the different derivatives look like when you graph them. And so we'll start with the function and talk about what its derivatives graphs would look like. And then we'll also work backwards where we have the graph of a derivative, and then we have to work backwards to determine what the function looks like. So something to keep in mind is that a function tells you the y value, and that means it's the height. How high up or down do I put my dot? That's what the value at a particular x. How high up should I put my dot? The derivative tells you the slope of the tangent line, and so this is telling you what angle is my curve at a certain point. Keeping in mind that we have angles that are positive slopes and angles that are negative slopes. And the second derivative tells you the concavity. And this basically tells you concavity. This basically tells you if it is shaped more like a smiley face or more like a frowny face. If you think about what a smiley face looks like, this is concave up. So this tells you that your second derivative is positive, whereas a frowny face tells you that your second derivative is negative. And the idea here is that as I move from left to right along a smiley face, my derivatives are steep negative, flatter negative, 0, flat positive, and then a steep positive. As I move from left to right along a smiley face, my derivative is increasing. That's why the second derivative is positive, because the second derivative tells you how does the first derivative change. And the first derivative tells you the slope. So if the second derivative is positive, you know that the rate of change of your derivative is positive. In other words, you know that your slope is increasing. Notice that you can have something be concave up and still be a decreasing function, like on the left side of the smiley face. And similarly, you can have something be concave up and be an increasing function. You can have something be concave up and be stationary, be flat. Very similar interpretation as you move from left to right along a concave down curve. You have steep increase, flatter increase, 0 slope, flatter decrease, and a steep decrease. As I move from left to right along the concave down curve, my derivative is decreasing more and more and more. So let's put some of those ideas together with an example of a squiggle. So let's say I have a function that does something like this, and I want to graph what its derivative looks like. The derivative will be a graph that shows the slope of this red curve. So why don't we use purple for my derivative here? What I notice is that I'm going to chop it up into intervals. What I notice is that right up until here, my function is going up. And so that means up until that point, my derivative is positive. Oops, let me switch to purple. Up until that point, my derivative is positive. And at the point where my red function is flat, the red function would have a tangent line that looks like this, and this has a slope of 0. And that's why my purple graph has an x-intercept at that point. Then I look for the next flat point, which is right about here. In between these two black marks, my red curve is going down, and that means that those tangent lines would be negative. It goes down pretty steeply, and then it goes flatter, and it reaches 0 right there. Then it goes super steep, so that's a big positive number, and then it hits back down to 0 right about there. Now it decreases, but not too much, and it goes back till it's flat right about there. And from there on out, it's increasing, so my derivative is positive, but it seems to kind of flatten out like that. So this purple curve is sort of a possible answer for what the derivative could look like. I was really guessing at exactly how steep it was, and I didn't put a scale on the y-axis. So if I had actual scales on the y-axis, I could get a more accurate derivative by estimating what the slope is between the given points there. But the key takeaway from this example is really just that when f of x is flat, f prime of x equals 0. And so this gives you a really key takeaway that um, the points where f prime of x equals 0 could be maxima or minima. And I want to emphasize the word could. I'll show you an example in a second where I have some points where the derivative is 0 that are not maxima or minima. In the example I just gave you, every time that my derivative was 0, every time my purple graph hit the x-axis, my red graph had either a peak or a valley. So I'll show you another example here now. We're going in the other direction. I'm going to start with a purple graph. I'm going to start with a derivative. And some of these x-intercepts are not going to be maxima or minima. So here is my purple graph. And now what I'm going to do is draw a red graph that could be the function whose derivative is the purple graph. What I notice is on this first chunk, the derivative is positive. So my red graph should be increasing. Here's a graph that's increasing, 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 and it's starting to flatten out until right where the purple graph hits the 0, my graph is flat for my red graph. Then my purple graph is negative, so my red graph is going down, and it's at its steepest point at the lowest value of the purple graph. Then it's still decreasing, but it's flattening out even more until it reaches here. This is going to be the minimum value. So I'm trying to indicate that the steepest point was in there and it's flattening out towards there. Here's the minimum. It's a little hard for me to draw that. Then the derivative is positive, so my red graph is increasing, increasing, increasing. Increasing still, flattening out here. Completely flat right below the x-intercept. And then the derivative goes positive again, so it increases, increases, increases. At this point right here, we have f prime of x equals 0. Here we have f prime of x equals 0. And here we have f prime of x equals 0. But I want you to notice that this one is a maximum, and this one is a minimum, and this one is neither. Think about what's different about the graph of the purple, the derivative compared to the other ones. Well, here on the purple graph, we go from a positive to a negative. And you can see that we went from increasing before, then decreasing after. If you go from increasing to decreasing, that's going to give you a maximum. Similarly, we had decreasing before and increasing after. That would be a minimum. But it is neither when you have increasing before or increasing after. Or, of course, you could have decreasing before and decreasing after. And those are called stationary points. Okay? So, what we talked about here was starting with a derivative and working backwards to get a possible sketch of what the graph could look like. I could also have drawn basically the same shape. Imagine that this is a parallel curve. And this would be exactly as correct of a possible response. It turns out that for a given derivative, there are infinitely many possible functions that could have that graph. Because think about if you had two functions, one of them was f of x plus 5, and another function was f of x plus 17, and another function was f of x minus pi. All of these are going to have the same derivative. They're all going to have the same purple graph. And so that's the idea, that I could have a whole family really of parallel curves, all which have the purple graph to them. Okay, and I'll finish out this video showing you something about the second derivative, which is something I mentioned at the beginning of this video. So if I have here a function, let's have it be something relatively nice, like this. What I can see is that in this area right here, it's concave up because it looks roughly like a smiley face. So I know that my second derivative will be positive here. In the middle section, it looks roughly like a frowny face. I know my second derivative will be negative. And then it finishes out the rest of it with a smiley face. So concave up, concave down. Sometimes I'll abbreviate it concave up, concave down, concave up. So let's first draw the purple derivative. We have a function that is decreasing until here. So I have a derivative that is negative until there. Then we have a derivative that is positive until there. Then we have a derivative that's negative until here. And then we have a derivative that's positive there on out. So something more or less like that. So that's the derivative. Then let's draw our second derivative. So all I'm going to do is play the same game I just did, but looking at the purple graph. So I'll draw my second derivative in orange. This is increasing. So I have a positive second derivative. It's increasing, it's increasing, it's increasing, it's increasing, it's increasing until here, because that's the peak of the purple. Then it's decreasing, 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 decreasing until here, because that's the valley of that. And then it's increasing there on out. So it probably would look a lot smoother, something more like this. But the point is that if you notice where I drew my concave up and concave down boundaries matches where my orange graph is above or below the x-axis. So that's sort of the basics of how you draw the graphs of derivatives and second derivatives. And in the second video, I'm going to talk about how you actually use some of the equations to identify these points. So please comment, ask questions if there's anything that's confusing.